Waiting time. Okay, so can you guys see my screen now?
Yes, sir.
Okay, so great. Okay, so just give me a thumbs up just to let me know that you guys are already in front of your computers. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 11. All right, so 11 out of 14. Okay, so yeah. So we now have here VA minus VB. So VA minus VB is our voltage drop or the voltage across this R1. So are we clear so far on how did we get this VA minus VB divided by R1 right here? Anyone? So just give me a thumbs up just to let me know that you were able to get this one. All right, so how about raise your hand if you didn't get it? None. So there were only two who gave me thumbs up. So I'm pretty sure that most of you are confused or, you know, maybe still didn't know how did we get this expression right here. So again, this one came from the Ohm's law formula. So I is equal to V divided by R. So if you're going to get the I1, so I1 is equal to V1, of course, divided by R1. Wherein the one that we're talking about, the V1 right here, this one is actually the voltage drop or the voltage across R1. Okay, wherein in order for us to get the value of VR1, okay, so we can use this uh, rule wherein we have the higher voltage lesser the lower voltage. Okay, wherein the higher voltage in here is the VA and then the lower voltage is VB. Now again, how did we know that the higher voltage is VA and not VB? Because if you guys are going to take a look on this one, okay, assuming that we have 10 volts in here, okay, so we already know that VA has a 10 volts, and as soon as it passed through this, resistor right here, of course it will give us a voltage drop with a value of we didn't know yet. Okay, so you already know that at this point, VB node VB, this one now has a lower voltage than VA. Okay, so that is why we have here VA minus VB, which is equal to our VR1. And if you guys are going to take along this one came from here. And then if you're going to substitute this VR1 right here, you will get VA minus VB divided by R1, which is now the same with this one. So I hope that one now is clear. So is everything okay now? Okay, how about the others? Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So 8 out of 15 maybe? Or 9 out of 15. So at least half of you were able to get this one. Yeah, anyway, so let's proceed to our I2. Okay, so just get this one since, so again, this is our reference. Okay, so this is already our I1. Okay, next one is the I2 right here. So same concept. So if we have I2 is equal to V2 divided by R2, wherein V2 right here is actually the VR2 or the voltage drop across R2. So we have here VR2. So the same concept in getting the VR2, we have here the VH, higher potential voltage minus the lower potential voltage. So for the R2 right here, so as you guys can see, we have here VC. okay, receiving a 20 volt. And at this point, so of course, it will leave a voltage drop. And then upon reaching VB, so VB now is lesser than VC. So we already know that VC is higher than VB. So in here, we could say that VR2 is equal to VC minus VB, okay? Which is now the same with our VR2 right here, okay? Wherein you can now use this IT right here to put it as our final expression on this uh, solution or expression. Okay, so we have here VC minus VB divided by R2. Okay, so are we clear? Are you guys able to follow? Okay, only three? What about the others? So 4, 5, 6, 6 out of 15. How many are we? Yeah, 15. 6, 7, 8, 9. So 9 out of 15. Okay, that's good. Okay, so in here, this is one thing that you guys need to know. Okay, so in nodal voltage, okay, the one that is connected to, the negative part, okay, of our batteries or voltage source, that is the one that we call the reference node or the ground node. Okay, so as you guys can see right here, the one that is connected on the negative side is this node B, and then the same with this one on the negative side or the electron side is this D. So we could already say that, as we all know, ground is always a 0 volt, okay, or the reference node is always equal to 0. So in here, we already know that VD is equal to 0. So we can actually use this that one already. Let me just move it right here so we can have more space for our I3. So the last one is minus I3, okay, wherein I3 is equal to VR3 divided by R2, okay, wherein VR3 right here, so the same concept, we have the higher voltage minus the lower voltage. So as you guys can see, we already know that VB is 0, so VB has at least a little bit value of voltage, so VB is our higher potential voltage. So VB minus, okay, VB, okay, which is actually 0, okay, divided by R2. And you can now substitute this one in here. Okay. Oops. Is this R2? No. R3. Sorry. This one is R3 also. So for the I3, we have here VB minus VD, oops, divided by R3 is equal to 0. Okay. And then from here, you can now substitute the given values, okay, of those uh, variables. So we already know that VA is equal to 10 volt, okay, and VB, so we don't know the value of VB since, it will be finalized once we already have the values of everything. Okay, so let's just leave it as VB. And then R1 is 10 ohms plus. So VC is 20 volts because that is the one that is passing through this node. So 20 minus VB, so we don't know the value of VB, so we'll just leave it like that. And divided by R2, which is 20 ohms minus. So VB, so we don't know yet. All right, so let me just make everything capital for consistencies. And okay, let me erase this one and make it capital. This one is VD, okay? And as you guys may already know, VD is equal to 0, so we could just put here, or we could just leave it as like that since it will not affect the value of VB since it's equal to 0. So minus VB divided by R3. So R3 is equal to 40 ohms is equal to 0. And as you guys can see, we only have one unknown variable. Okay, so if we only have one unknown variable, so we can now solve for the value of that unknown variable. So in my case, what I will do is I will multiply this 1 by 40 to eliminate the denominators. So 10 or 40 divided by 10 is 4. So that's times 4. 4 times 10 minus VB. Okay, plus. So 40 divided by 20 is 2. So that's multiply to 2. 2 times 20 minus VB. Okay. And then 40 divided by 40 is 1, or this will just simply cancel, minus VB. Okay, is equal to 0. And then from here, you can add similar terms, or you can distribute first, rather. Okay. So 4 times 10 is 40 minus 4VB plus 2 times 20 is 40 minus 2VB. And then minus VB is equal to 0. And then from here, you can now add similar terms. So 40 and then 40, so both of them are positive, so it will give us 80. And then minus 4 and then minus 2VB and then minus 1VB, which will give us negative 7VB is equal to 0. And then from here, you can transpose this one on the other side, 7VB, and then you can now solve for the value of VB. VB is equal to 80 divided by 7, which is equal to 11.43, okay, volts. So there you go. You now have the value of VB. And then since we already have the value of VB, we can now solve for the value of I3. Okay. So in here, you can actually already solve the value of uh, the I1 and then the I2 since VB is now already given. You can just use this formula. Okay. So let's try to solve the value of I1. So I1 is VA minus VB divided by R1. So let's see what is the result of that one. So VA is 10 volts minus VB is 11.43, okay, divided by R1, which is 10. So whatever is the result of this one, that is our I1. Okay, 10 minus 11.43 divided by 10. So this one will give us negative 0.143 amps. Okay, so this is our I1. And then for the I2, okay, so again, you can get this one, VC minus VB divided by R2 to get the value of I2. So VC is 20 minus VB is 11.43 divided by, what is our R2? So it's 20. So this will give us a value of 0.4285 amps, which is now, this is your I2, or equal to I2. And then for the last one, for the I3, so that is VB, okay, divided by 40. So VB is 11.43 divided by 40. 11.43 divided by 40 will give us a result of 0.28575 amps. Okay, this is now our I3. Alright, so there you go. And then from here, you can also look for the VR1, VR2, and then VR3 since we now have the individual currents. So I will not show those anymore since they are very obvious. So VR1 is equal to I1 times R1. Okay. So VR2 is equal to I2 times R2. And then VR3 is equal to I3 times R3. All right. So yeah, actually our main goal here is just to get the, the voltage across VB and then the current across that VB, which is this one, 0.28575. So were you guys able to follow so far up to this point? Okay, very good. So three only. What about the others? 3 out of 14, 4 out of 14, 5, 6, 7, 8, 9. Okay, very good. At least half of you were able to get the idea. Okay, so if we are going to compare that one, oops, not this one right here. So yeah, the I3 is 0.286 amps. And there you go. So this one is 6, so it only gets the 3 decimals. And yeah, and VB is 80 divided by 7, wherein 80 divided by 7 is equal to 11.43, okay, which is this one. All right. And then the rest are just, bonus, wherein you can solve for the I1, I2, I3, VR1, VR2, and VR3. Okay, so that's it for the first example. So let's have one more example. So in here we have a voltage source and then a current source. So before we are only dealing with two voltage sources, but right now we are now going to deal with a voltage source and then a current source. So in here, same thing. We need to find the I1, I2, I3, VR1, VR2, VR3, and then VA, VB, and then VC. Okay. So notice that VD is, didn't include here because VD is always equal to 0. That is our reference node or our ground node. Okay. So in here, again, just same method as apply KCL first, wherein we have here I1 going into VB, I2 going into VB, and then I3 leaving, okay, which will give you this result right here. And then if you're going to transpose this one on the other side, it will give us I1 plus I2 is equal to I3. Okay, so are we clear so far up to this point? Again, okay. But anyway, so I hope everything is clear on this one since this one is super straightforward. And then again, what we are looking for is the value of VB because once we have solved the value of VB, we can now solve the value of VR1, VR2, VR3, I1, I2, and I3. Okay, so the same method. Okay, so we're going to apply the formula of I is equal to V divided by R, and then in here we're going to look for the I1 first, right here, which is equal to V1 divided by R1, or this V1 right here is actually our VR1 or the voltage drop across R1, okay, wherein I1 is equal to VA minus VB. So again, the same concept. We have here VA minus VB because we know that VA has a higher voltage than VB. Okay, so we can use this one already for our I1. So VA minus VB divided by R1. And then for the I2, so the same concept. So we have here VC minus VB divided by R2. So there you go, VC minus VB divided by R2. And then for the I3, okay, so we have here uh, VB minus VD divided by R3, which is now this one. And then from here, you can now substitute the given values or the given variables. So VA is 30 volts, okay, minus VB. So VB, we don't know that one, so we'll just leave it as it is. And R1 is 5 volts, I mean 5 ohms, which is now this one. And then for the I2, so notice that I2 is already given as a current, so we don't need this one anymore. Okay, we can just simply say that I2 is 3. So that is why we have plus 3 right here. And then for the VB, so just leave it as it is. So since we don't know the value of that one. And then for the VD, so just minus 0 divided by 3. Okay. So are we clear so far up to this point? Can you guys still follow, or am I too fast?
Yes, sir.
Okay, all right. So if you have a question, so again, feel free to raise your hand. Then let's talk about your concern. All right, so no question. All right, so let's proceed to the next solution. So in here, my goal here, and why did I put here 15, is I wanted to eliminate the denominator. Okay, so just multiply everything by 15, and then you will get this one. So 15 divided by 5 is 3. So 3 times 30 is 90. And then just multiply that 3 to this VB, so it will give you negative 3 VB. Okay. And then for the next one, so 15 times 3 is 45. And then for the last one, so 15 divided by 3 is 5. So it will give us 5 VB. Okay. And then from here, just add similar terms. So 90 plus 45 is 135 minus 3 VB is equal to 5 VB. And then from here, we can transpose this on the other side so that we can add similar terms. So 135 is equal to 5 VB plus 3 VB is equal to 135 is equal to 8 VB. Okay. And then from here, we can now solve the value of VB. So VB is equal to 135 divided by 8, which will give as a result of 16.875 volts. So I hope you guys are using your calculator right now to verify whether this one is correct or no. So please check. Do you guys have the same result, 16.875 volts for our VB?
Same, sir.
Very good. So now, since we already have the value of VB, okay, we can now solve for the value of I1, I2, I3. So any of those that, you can solve first. But in here, we can now solve for the value of I1, okay, which is, using this formula, we have VA minus VB divided by R1. Okay, just substitute everything and then you will get 2.625 amps. And then for the I3, so the same concept. So we have this expression right here for the I3, whatever is the result of this one. Okay, 16.875 minus 0 divided by 3. That is the value of I3, which is 5.625 amps. So the only risky thing in here is if your VB is incorrect, okay, if your answer in VB is incorrect, everything now is also incorrect. So just be careful when it comes to solving for the super node voltage in here, which is the VB. Okay, and then for the I2, again, you can use this expression right here, or you can just simply apply KCL, okay, which is, same with this one, I1 plus I2 is equal to I3. So solving for I2, we have I3 minus I1. So 5.625 for the I3 and then 2.625 for the I1, which is now equal to 3 amps. And then from here, we can now solve for the value of VR1 and VR2 and VR3. So VR1 first, so I1 times R1. I1 is 2.625 and then R1 is, where is that one? 5 ohms. So 2.625 times 5 will give us 13.125 volts. Okay, or you can actually use this one. Okay, so going back to our main reference, so we have VA minus VB. Okay, for our voltage drop. Okay, so you can also do that one. So VA is equal to 30 minus VB. Okay, where is our VB? Minus 16.875. So 30 minus 16.875 will give as a result of 13.125 volts. Okay, so please check everything. So I'll give you guys 1 minute to recheck our answers before we proceed to the VR2 and VR3. Okay, so is everything correct? My 15 right here, Miss Chelsea, on the multiplication. Okay, so in here I just multiplied 15 because my goal is again to eliminate our denominators. Okay, so again 15 divided by 5 is 3. So 3 times 30 is 90. And then 3 times negative VB is negative 3 VB. Okay. And then same, so 15 times 3 is 45. And then 15 divided by 3 is 5. So we have here a multiplication of 5. So 5 times VB is 5 VB. And then from here, you can now simplify everything. Okay, just add similar terms, etc., etc., and then you will get this one. All right. So any other concerns? Okay, you're welcome, Miss Maxine. Okay, how about the others? Were you guys able to verify whether our answers in I1, I2, I3, VR1 is correct or no? Okay, why is my PC super lag? Okay, so there's already two of you who already verified this one. Okay, so I hope the others were able to follow, okay, everything. Okay, so moving on, we have here for the VR2 and then the VR3. So for the VR2, just, as long as you already know the value of I2 and R2, which is 3 times 4, it will give us 12 volts. And for the VR3, so the same method. So I3 is 5.625, and then R3 is 3 ohms, which will give us 16.875 volts. Okay, wherein if you guys are going to take a look at this one, so for VA, VB, and then VC, so VA is 30 volts, and then VC is 12 volts. Oops. My bad. Okay. So see, so at this point, okay, so this is not 12 volts rather, because this one is I2. Okay, my bad. So I mislook on this one as 12. So in here we have to solve for the value of VC, since the only given is 3 amps. So solving for VC, okay, we have here VA, I mean the original equation right here. Okay, and then just substitute everything and then just leave the VC right here, since we don't have the value of VC. Okay, and from here we will get this one as a result, just by substituting all of the given values. Okay, and then after that, so again our goal here is to eliminate the denominator. Oops, wait a second, what did I do next? Okay, so not yet. I have simplified this one first. So 30 minus 16.875 divided by 5 will give us 2.625. Okay. And then VC minus 16.875 divided by 4 will stay as it is, since we cannot do anything about this one. And then in here, so 16.875 divided by 3 will give us 5.625. And then in here, we only have one remaining denominator. So just multiply that one by 4 to eliminate this denominator right here. So 4 times 2.625 will give us 10.5. And then 4 divided by 4 is 1. So just copy as it is. So VZ minus 16.875 is equal to, so 4 times 5.625 will give us 22.5. Okay. And then from here, you can now add similar terms. So 10.5 minus 16.875, or what I did here is I transpose everything. Okay, so VC is on the left side, and then everything that is not the same is on the right side. Okay, so in here we have 22.5 plus 16.875 minus 10.5. And then in here, just simplify this one. I mean, not simplify, just solve this one using your calculator, and then you will get 28.875 volts. Okay, so this is the solution using our main expression. Or you can, use the VIR, okay, or the VR2 is equal to I2 times R2, okay, because in here VR2 is VH minus VL is equal to I2 times R2, wherein VH is VC and then VL is VB, so retaining the I2 and R2. And right here, VC minus, so VB is 16.875 is equal to 3 for the I2 and then 4 for the R2. And then again, just solve this one and then just transpose this one on the other side. You will get 12 plus 16.875. So which will give us the same answer, 28.875 volts. Okay. So yeah, that's it for this example number 2. So I hope you guys were able to follow on how did we solve the VC. So we have two ways for that. Okay. So let me just ask you guys, are you guys able to follow? Is everything clear so far? Okay, so 1, 2, 3. What about the others? All right, so it's a good thing that most of you were able to get this one. Okay, so that's it for this example, and then here's just a conclusion. So generally, nodal voltage analysis is more appropriate when there are larger number of current sources around. Okay, so if we have maybe purely voltage sources, then you can use superposition theorem. But if there are more current sources, then nodal voltage is much more preferred when it comes to solving. Okay, solving for the unknowns. And in here for more examples and explanations, so again, you can visit those 3 YouTube links. Okay, so this will give you another explanation, another example, to just again to clear up your questions or clear up your minds when it comes to understanding the nodal voltage analysis. So yeah, that's it for this module, and this is already our last module, and we still have one remaining meeting, okay, which will be on Monday. So we will not meet next meeting anymore. So I will give this one as your free day to finish the 2 quizzes that I gave to you. So the same with the laboratories that I am giving to you guys. So later on, I will add one more laboratory, which is for Maxwell loop method. Okay. So the due date of that one is also May 24. And then your midterm exam will be on May 27, Thursday. So the coverage of your exam is, of course, everything that we have discussed from Module 1 to Module 6. And since we don't have quizzes for, yeah, we don't have quizzes for the superposition theorem and the nodal voltage analysis, so I would highly suggest you guys to, spend a lot of time in doing some practices. So just visit this website right here, visit this site. Oops, my bad. I wasn't able to include a link or a practice exercise for superposition theorem. Anyway, you can find a lot of examples in Khan Academy, okay, or even in YouTube's. So there's a lot of tutorials in there which will teach you different kinds of examples when it comes to superposition theorem and nodal voltage analysis. And also don't forget to answer this one, the case study number 3. So the due date of this one is also in May 24. All right. So the same with your case study number 2. Okay, so we now only have 1 minute left. So do you guys have a question so far? Or if none, just give me a thumbs up. Okay. So yeah, those who gave me a thumbs up, you may now go. And yeah, so let's just meet again next week after your midterm exam. Okay. And goodbye and thank you guys for coming. So if you guys have a question in the future, feel free to message me anytime. Okay.